Hello, my name is Firoz Mahmood, and I will be going over the weaknesses and limitations of three-dimensional imaging with you today. These are my disclosures. The outline of the talk is that we'll be going over the transducer design, the stages of 3D image formation, resolutions in 3D imaging, and the importance of knowledge of the holy triangle of imaging, parallel processing, R-wave gated imaging, parallax error, and then the final word on what the limitations and the weaknesses of 3D imaging are. Let's go with the transducer design first. We need to understand the design limitations of the 2D and 3D transducers to move any further. The traditional 2D transducer has about 125 piezoelectric crystals sampled at any given moment in time. They generate a 2 millimeter thick scan plane, which is sparse arrayed, which means these crystals are spread over a certain area in the transducer for thermal limitation, and are intermittently sampled, which means they're not stimulated all at the same time. Now, we all knew that to analyze a structure as complex as heart, we need to have a three-dimensional imaging transducer, but the limitations were purely technological, and that consisted of lack of availability of electronics, thermal limitation of stimulating so many crystals, the size of the transducer, and finally the beam formation, which I'll get to that in a second or so. So the traditional transducer led to a very narrow beam, which was almost just as wide as the footplate of the transducer. And by steering the beam electronically from side to side, that is, moving the beam from left to right by sequential activation of the piezoelectric crystals, we were able to achieve a far wider footprint or far wider scan plane than the footprint of the transducer. Now that has some limitations on the lateral resolution, and that plays a great role in three-dimensional imaging resolution determination. That's why I brought up this point. Then, in early 2000s, the matrix array fully sampled 3D TE probes are introduced. These consisted of having almost 2,500 crystals put together in a matrix array, which were continuously and completely sampled, all of them, so they were not thermally limited. So this was purely a technological marvel, logarithmic scale development and enhancement of the existing two-dimensional TE probe. So that was the first thing. Now, how did they achieve this whole process? Because obviously there's a lot of information coming in, and there's also a lot of electrical channels that had to convey this analog information to be converted into digital signals up in the ultrasound system. The way it was achieved was by creation of a micro beamformer or a pre-beamformer, which was essentially conversion of analog to digital first stage conversion that used to happen in the ultrasound system would happen in the head of the transducer in the 3D probe. So that was the first innovation, and that was electrical group and combine the electrical output of small arrays of elements to a single wire, which means they were able to drastically reduce the number of wires and cables going through the shaft of the TE probe. And so therefore a single patch could have almost as many as 25 crystals feeding into it at the same time. So therefore, it allowed to achieve same quality as a fully sampled array probe with 3,200 wires and 32 analog to digital converters. So first stage conversion of signal that used to happen in the ultrasound system would happen in the ultrasound TE probe and the ultrasound head now. So that was the first technological innovation to create a microbeam former. So as a result of that, the phased array transducer that just puts out a ultrasound beam in the azimuthal azimuthal dimension was able to sample in 3 dimensions, which means not only in azimuthal but also in the elevational plane. Now when that happens in real time, you see what it does is that this plane not only is steered laterally but also in the elevational aspect. And as a result of that, what is generated is what is referred to as a frustum and not a scan plane, which is it is like an inverted pyramidal shaped scan plane, which is the volume of pulses that is generated not only moving from right to left, but also above and below to give it a three-dimensional perspective. Now, as a result of this thing, this is referred to as a frustum, a thick scan plane with length, breadth, and an elevational aspect, which is also probe response. So that's what 3D ultrasound system produces. Besides, producing a frustum, it also has the ability to generate multiple orthogonal planes at multiple two-dimensional scan planes at the same time, which I believe is one of the best features of these three-dimensional probes, is not generation of a frustum, but generation of simultaneous orthogonal planes in multiple dimensions and multiple directions at the same time. We'll get to that also in a second. Now, having said this thing, what are the stages of 3D image formation? Because that's where the devil lies in the details of what are the limitations of three-dimensional imaging. So the three-dimensional imaging is based on a very famous mathematical principle of three-dimensional reconstruction, and that is called the marching cube principle, which means every complex surface is divided into multiple cubes, and for each cube it is determined what part of that surface is within the cube, what is intersecting the cube, and what is outside the cube. As a result of generation of these infinite number of cubes on a complex surface, we are able to accurately plot the topography of a complex shape by knowing what part of surface is within the cube, what is intersecting with the lines of the cube, and what is outside the cube. And each cube then marches along the entire topography of a complex surface, and therefore we are able to broadly know the outside shape of a complex three-dimensional object. So this is referred to as the marching cube principle. This is how the data is collected and collated and produced for further analysis once it has been acquired from the tissues. So once it is acquired from the tissues, the stage that it goes as the first stage is called conversion, which means accurate reproduction in the Cartesian coordinates of the location of the acquisition of data in a digital space, and that's called conversion. So after conversion is the next most important step and the major limitation of three-dimensional imaging, and that's interpolation, which means the grayscale, based on the adjacent grayscale, the gaps in the data are filled in with information which is based on adjacent grayscale images, and that's referred to as interpolation using artificial intelligence algorithms. Then comes the smoothing, which means right corners are smoothed out, curvatures are introduced, and we tend to have a sort of a volume to the data that we acquired. And lastly is segmentation and rendering, which is again a complex algorithm to produce and demonstrate it and ready it for display on the screen. Now, the most important word that we've learned so far is interpolation, which means the volume of data that is acquired has a significant number of gaps of information in it, and they are filled in with adjacent grayscale image, and that's referred to as interpolation of the missing information. Now, depending upon what the size of the volume that we want to interrogate, which means the bigger will be the gaps in the data, and the more will be the interpolation, and more will be the likelihood of making errors and generation of artifacts. So therefore, three-dimensional imaging, or the three-dimensional data set that we acquire, is not a continuous or completely filled in from real data. There's a lot of interpolation in it, and the size and the magnitude of that interpolation depends on the line density and the size of the sector that we are interrogating at any given moment in time. And therefore, this brings us to the resolutions in three-dimensional imaging, and finally, the knowledge of the holy triangle of imaging. The resolutions that are spatial, that are more important to know, are the axial, which is front to backwards, the lateral, the side to side, and elevational, which is above and below, ability to distinguish objects. Temporal resolution is essentially knowing the precision, the speed, and the direction of the motion of an object. Now let's see what determines each of these resolutions and how they impact three-dimensional imaging. Spatial resolution is purely a determinant of line density, which is fixed for a transducer. The number of lines coming out of a transducer is fixed. The way we increase or decrease the line density is just purely changing the sector size, which means reduction in sector size is what we are increasing the line density. There are some systems that allow you to reduce the number of lines that you're getting at any moment in time, but you cannot go beyond the maximum line density of any given transducer. Temporal resolution purely is determined by the go return time, which means how long it takes for the signal to go and come back, the sector size, how much information we are computing at any given moment in time, and finally line density. And that again, the more information we provide the transducer, the harder and the longer the system is going to take to compute to precisely identify the direction and the total speed of motion of an object. Lower frame rate, lower temporal resolution, when you have a longer go return time. When you have a shorter go return time, which is the imaging depth, you have a higher frame rate and a higher temporal resolution. For the same sector size, increasing the line density reduces frame rate and temporal resolution. That's very simple and straightforward. So therefore, the fundamentals of 3D imaging are how much you want to see, which is the beam width, and that's the sector size, how good you want to see it, which is the line density and the spatial resolution, and how fast you want to see it, which is the frame rate and temporal resolution. This reminds you of 2D imaging. So it essentially has the same limitations and perhaps more than that of a traditional 2D imaging. Let's just say you want to see too much. Well, that's easy answer. That's this increase in sector size. But once you increase the sector size, you are reducing your line density. And depending upon whether you're able to change or reduce the line density, you have to have either more interpolation, which means your spatial resolution will go down. And if you want to reduce the spatial resolution, you'll have to increase the line density. In that case, your temporal resolution will go down. You want to see too good, let's just say. If you would reduce the sector size, then your line density will increase, and obviously your spatial resolution will increase, but at the cost of a wider sector size. So reduction in sector size really determines and that has a lot of impacts on temporal resolution, and that really depends on whether you reduce the line density or keep the line density as the same, which means the frame rate could go down or up depending upon the various permutations of line density and sector size. Every action you take has to have some consequences. Let's just say you want to see too fast. You have to reduce the sector size and reduce the line density. You cannot have best of everything at the same time. Having said this thing, so increasing and decreasing the line density, increasing the sector size, reducing or increasing the imaging depth, they all have impacts on your line density. Therefore, spatial resolution is determined by line density. Low line density implies low spatial resolution. A high line density implies high spatial resolution. But in this scenario, there will be more higher temporal resolution. And in this scenario, there will be lower temporal resolution. Sector size is field of view. So therefore, it really depends on how and what you want to see. If you want to improve and optimize your temporal resolution, there will be a sacrifice on sector size and spatial resolution. The same goes for spatial resolution. And lastly, having a large sector size will obviously reduce your spatial and temporal resolution simultaneously. Therefore, it brings us to the holy triangle of imaging, which means you cannot have best of everything in three-dimensional imaging. You have to know what you really want to see, and that's either the sector size, spatial resolution, or temporal resolution. Now, to do away with this thing, what was developed is referred to as parallel processing, which means that in three-dimensional imaging, the major challenge is frame rate, which means your temporal resolution gets hugely compromised once you increase the sector size, not only in the lateral direction, but also in the elevational dimension. There's a significant reduction of your sector size. And therefore, by increasing the sector size in any dimension, you're also compromising on your lateral and elevational resolution. These are the two major challenges in three-dimensional imaging. So what they found was a method called parallel beam formation or parallel processing, in which system transmits one large beam, and then selectively it samples more of the returning signals, and therefore there are multiple received beams at the same time, but only from the region of interest, and that's called parallel beam formation or parallel processing. So what it does is, it's analogous to taking a picture of a huge landscape, but then focusing more on certain regions of interest within that wider landscape so that you get more information from that specific location and ignore what is not that important for you. Now, this is kind of a little difficult concept to understand, but just let's look at this en face view of the mitral valve. And you can see that the temporal resolution, that the frame rate 29 Hertz is more so in the center of the beam, the point line of coaptation, the anterior and posterior leaflet. But the very periphery of this image, which is the largest sector size, the frame rate does not match, or the image or the motion that you're seeing is not as precise and not as clean as you're seeing in the middle, because this image has been generated from parallel beam formation, which means while it sends out a larger beam, but there's more selective sampling from the center of it to increase and enhance the frame rate of this image. Therefore, parallel beam formation has its pros and cons. It increases frame rate, but it increases the size of the transducer, the size of the beam, the cost and the power of the systems. It increases width because you have to send out a very large beam and therefore increase signal to noise ratio, and you have to have more contrast. And finally, the parallel beams steer farther and farther away, and there's greater attenuation and lose power. This brings us to the formula to determine the frame rate. That beings is 1540, your go return time, which is constant, 1540 meters per second. The number of parallel beams that you receive will obviously increase your temporal resolution and frame rate, but the volume width and the volume depth are the two most important determinants of your frame rate, which means as you want to look more and you want to look deeper, your frame rate, your temporal resolution will be significantly compromised. So examiner in a three-dimensional imaging can change the frame rate by changing the depth and width of a beam. So they are significantly more compromised than two-dimensional imaging, that is your lateral resolution and your frame rate. However, axial resolution is not relevant to frame rate and therefore is not much impacted in three-dimensional imaging, as is the lateral resolution and frame rate in these patients. So is there a way around this impediment? And that would be stacking of multiple 2D slices together acquired over a certain period of time, and then going around this problem of having a lower frame rate in these patients. And that is referred to as R-wave gated imaging, which means you have stacking up of multiple 2D slices, intervening gaps extrapolated by the computer-based algorithm of grayscale imaging on adjacent things, and then finally putting them together into one bigger image. And it is called interpolation or concatenation, which is creating new data points that are within the range of known or discrete data points. This is a complex definition of fill in the blanks. It's essentially filling the gaps based on adjacent grayscale imaging. And what it consists of is stacking of 2D slices, one on top of each other, and then once they have all been acquired in a certain frame of time in a certain space, they're all put together to create a volume, and that is referred to as concatenation. Now, the challenges of concatenation of intracardiac structures are significant, which means there's a translation motion of the heart, there's respiratory motion as the patient is breathing, and finally, there's systolic and diastolic excursion of leaflets that is happening continuously, and you have to account for that, which means for concatenate intracardiac structures, you have to acquire slices of cardiac anatomy that are at the same position of the heart and at the same time in the cardiac cycle. Now, acquiring spatial alignment, which means having them be acquired at the same space, is easy. No patient motion, suspend respiration, don't move the TE probe. But temporal alignment is more complicated. It is required that frame to be acquired at the same time in the cardiac cycle to be aligned with each other. And the ultrasound machine has to know when to start and when to stop acquiring the frame. And that's the only way to do this thing is through EKG gating. And that is, frames are acquired between adjacent R waves, and they stop acquiring frames on every R wave. In this fashion, multiple frames are acquired between adjacent R waves and are put together. And finally, a larger composite image of about 6 or 7 heartbeats is created, and that's called R-wave gated imaging. But as you can realize, the one important condition is a regular R-to-R interval, which means frames have to be equal between adjacent R waves over a longer period of time. Which implies that if the patient has a regular sinus rhythm and you are not moving the TE probe, the image is acquired not only at the same place in three-dimensional space, but also at the same time during the cardiac cycle. So the alignment becomes easy. So systolic frame get aligned with the systolic frames, and the diastolic frames get aligned with the diastolic frames, and that's called concatenation, and we can do that very well. However, the patient is in any arrhythmias or atrial fibrillation, then you're out of luck because this thing cannot be achieved that fashion. The last thing is the parallax error, which means these three-dimensional images as we see them on the screen appear to be three dimensions, but they are projections on a flat screen. There's a perception of depth, but there's no actual depth in the screen, and that's called a parallax error, and that's the reason we cannot make any linear dimensions on these images also. And a parallax error is referred to as an apparent change in the position of an object to the change in the position of an observer. Like you can see, if an observer sitting on Earth in early July looks at this green star, it appears to have blue stars in the background. However, as the Earth moves in January to this location, and when the same astronomer looks at the green star, it seems to have moved to have these red stars in the background. There's been no change in the position of this green star, only the change in the position of the observer that has led to these this change in the position of the star. That's the greatest problem with three-dimensional imaging. For example, you can appreciate this aortomitral angle in an anatomical illustration. The same can be appreciated in a tomographic two-dimensional scan of the mid-esophageal long axis window. You can appreciate depth in this en face view of the aortic valve, the angle between the mitral valve and the aortic valve axis, but you cannot actually measure it, and that's referred to as parallax error because it appears to have a depth into it, but there's no actual depth on the screen. So the final word is that it is also susceptible to all the artifacts that are traditional two-dimensional images, and only 3 times as much. And there are numerous more and more complicated artifacts of three-dimensional imaging, which are, and it is not devoid or not independent of any artifactual imaging. Lastly, it is a myth that patients with suboptimal 2D images can have optimal 3D images because all 3D images are made of the same physical principles as 2D images, and all 3D images are composites of multiple 2D images. The greatest impediment is the speed of sound is constant, that is 1540 meters per second, regardless of the quality of the system. So the go-around time of the transmitted beam, unless it becomes faster, there's no way of improving your frame rate for a given depth and a given sector size. Therefore, 3D imaging is great, but not perfect and not devoid of any artifacts and problems. Thank you very much.